Voilà, mesdames, messieurs.
Ladies and gentlemen, good evening. Welcome to this first conference of the Wright Colloquium on Science. My name is Thibault and I'm a scientific journalist, and I'm going to MC all these evenings throughout the week. As you know, we're privileged indeed, honored indeed, because we listen to fantastic speakers who come from all over the world to present their research results to you. This year, in keeping with our tradition, we are going to travel with our speakers in the solar system, in our galaxies and beyond, whilst remaining on our 2 feet, thanks to gravity. Gravity, as you know, regulates the way we stand, our posture, and which nevertheless remains quite mysterious. A week ago, the Chinese team came up with 2 different measurements with this constant of gravitation. Perhaps something you remember from your physics classes. As you know, there'll be 2 parts to our evening, as per usual. We'll listen to our speaker first. He's going to speak French, and he will be interpreted into English, and then there'll be a Q&A session during which you'll be able to put your questions to the speaker in French and in English, and we'll also have on the rostrum 2 additional speakers just to have an interdisciplinary discussion. So I'd ask you not to switch off your cell phones, just switch it on to silent, because you'll be able to put your questions in 2 ways as of now already. Of course, you can do this live to the speakers on the rostrum, but you can also use Twitter with the hashtag that's on the screen, hashtag Colloque Wright. Be able to put your questions on Twitter. We'll field them and ask our speakers to answer these questions. This is important for those who are in the other room and beyond, because we are got lots of people listening to the live stream, so you can put questions on Twitter. Before we get down to brass tacks, I'd like to give the floor to 2 people who are going to say a few words of welcome. First of all, the rector of the University of Geneva, Mr. Yves Flückiger. He has the floor. President, ladies and gentlemen, colleagues, obviously I'm very privileged indeed to welcome you this evening in this room, which is very full to such an extent we've had to open a second room. And obviously for us, for the foundation, it's a fantastic tribute to the foundation, given the interest that you show in this colloquium. And I'd like to thank the Wright Foundation having chosen the University of Geneva to organize these events. It's the 18th colloquium of the kind, and this year we're going to talk about gravity and gravitation. Everybody's heard about gravity and gravitation. It's a physical phenomenon which remains mysterious, and we will discover an increasing number of things about gravity and gravitation, and I'm very happy that we're able to share with the Wright Foundation this concern to make known the results of scientific progress. That's what the University of Geneva is about. That's what the Wright Foundation is about, to do all this extension work. And it's very important that we are able to do this with the Wright Foundation and other events and associations, to be able to share with you the knowledge that is expanding year on year. I'd also like to draw your attention to another event which has become very important for the city of Geneva, the Sound and Light show, which is on for a few weeks. Perhaps you've missed the 6 o'clock show. There's one at 8 p.m. again, but you can also see this Sound and Light show another evening, because it's a beautiful show. and it's shown on one of the oldest buildings of the University of Geneva. It's a fantastic show which enables us to highlight this beautiful building which is going to be renovated, and that's a fantastic opportunity for us. Again, I wish you a very pleasant evening, an excellent conference, and I hope you'll come back throughout the week to attend the other conferences. Thank you, Mr. Flückiger. Thank you, Mr. Rector. I'm now going to give the floor to Thierry Courvoisier, the president of the Wright Foundation. Mr. Rector, ladies and gentlemen, good evening. I'd like to thank the University of Geneva for enabling us to organize this event on its premises. It's always a pleasure to cooperate with the University of Geneva. We are, to some extent, part of the University of Geneva, so welcome to the Wright Colloquium this year. Another opportunity to share the results of scientific progress, because knowledge, if it's kept to oneself, is worth nothing. It's only if it's shared knowledge that it will be useful to others, and it's important for society as a whole, because knowledge which has just been acquired, which has just been developed, finds its place in our culture and therefore shapes our identity. We share between scientists and a wider audience, and it's an international event which allows us to express ourselves as citizens of the planet Earth and together to build a better world for everyone. So there's a lot at stake here, especially at a time where another round of elections are going to take place in Switzerland. So, Mr. Rector, ladies and gentlemen, I'd like to know whether you're sitting comfortably. Yes? It's not because I want to vaunt the comfort of the seats at the University of Geneva. It's because of gravity that you are able to be seated comfortably, and you feel this weight on your thighs as you sit in your seats, and it's a force that we are familiar with. You have to fight gravity to climb the stairs to leave the auditorium. That's what makes it so difficult when you are riding a bicycle uphill, and that's what makes you fall if you stumble. So it's a familiar force, but nevertheless it remains very mysterious. And those who are familiar with the works of Tintin know that the leaps that Dupont and Dupont happened upon on the moon are far more complicated, and when a planet becomes extremely dense, gravity stops light from escaping it. It's as if it were to create a black hole in space. Gravitation also creates waves that we've detected some time ago, and the characteristic of these waves is that they change the difference between two objects that do not move. Again, that's an interesting thought. So everything is down to gravity and gravitation, and therefore it allows us to detect matter that doesn't emit any light in the universe. And it is one of its properties that we're going to discuss this week as well. Finally, roughly after 100 years of hard work, it would seem that we're still incapable of giving a description of gravitation that is compatible with the description that we have come up with describing the other forces of nature. So gravitation is not only fascinating, but it can also be extremely practical and precious if we are to travel in the solar system towards objects where it doesn't exist practically. So all these aspects will be discussed this week by fantastic speakers, and I would like to thank them already now for their contribution throughout the week. The speakers will be introduced every evening by a professor of our region who is familiar with their work, and I would like to thank them for creating this link between the research that takes place elsewhere and the research that takes place this evening. Thank you, Olivier de Cibourg, for emceeing these evenings, and thank all those who worked very hard to organize this event. Ascension Lozano, Mrs. Cisbane, those in charge of technology, people in charge of security, and hostesses that allowed you to come to this evening's event. So I wish you a very enjoyable evening indeed.
Merci.
Thank you, Thierry Courvoisier. As Thierry has explained, we now are going to listen to an introduction of this evening's speaker, Michele Maggiore, who teaches physics at the Université of Geneva. Mr. Rector, ladies and gentlemen, it is a pleasure indeed to introduce the speaker for this evening, Thibault Damour. He's a world-known scientist. He is one of the most well-known scientists specialized in the field of gravity. When I started to prepare this paper, I discovered something which was rather extraordinary. Thibault's fascination for Einstein's work on an early age already started reading Einstein's papers at the age of 14. He then wrote an article for Princeton, and it was about a mathematical passage already at the age of 14, just to give you an idea of the coruscating brain that we are going to listen to this evening. Then he went to the École Normale Supérieure in Paris. He wrote his dissertation at the age of 22, and then he went to Princeton, where Einstein spent the last years of his life with Willier and others, and started working on very important aspects. I'm not going to take the wind out of his sails, but he discovered a binary pulsar, a fantastic system with an electron turning around another one, which is very important in the area of gravity. And this was discovered in 1974, and they were awarded the Nobel Prize for this discovery in 1993, if I'm not mistaken, because they were then able to test the extraordinary effects of relativity, but to be able to test them, they had to calculate them, and that's what Thibault did with his colleague Nathalie Derieuel. And I also worked on the physics of gravitational waves, and confusion reigned at the time. Einstein had even doubted the existence of gravitational waves in the 50s. We understood more or less that they existed, but if they are emitted in binary system, how can we calculate them? And it was very difficult. And Thibault started to research this question. And I find this aspect always extraordinary in Thibault's work. Is obviously of tremendous scientific rigor in all that he endeavors, and he then went on to solve more complicated problems after calculating the gravitational waves. He went on to even more complicated calculations, and we'll see his extraordinary technological capabilities and mathematical capabilities. Thibault's work have always been very important for Taylor's Nobel Prize, as well as for the discovery of gravitational waves of Liouville. They are mentioned in the motivation of the Nobel Prize. So I'm not going to dwell on this work any longer because we have a fantastic speaker. I'd just like to conclude by discussing other aspects of his personality. First of all, he's extraordinary when it comes to extension work. He wrote a book, If Si Einstein m'était compté, and then he also published a cartoon with an illustrator, and it's just been awarded a prize, the best cartoon. So I'm very jealous of his other capabilities. He's a fantastic concert pianist, and he's been awarded many, many prizes. And with some of the money of these prizes, he bought himself a Steiner piano. I am not going to dwell any further on his coruscating personality, but would like to give him the floor. You have the floor, Thibault.
Donc, ce soir, j'ai le...
So, this evening, I'm very pleased indeed to be able to make a presentation on gravitational waves and black holes. We're going to start with Einstein at the time when he discovered the theory of general relativity, which upset him for a number of years because it was very, very difficult indeed, as we can see from here, from the picture. So we're going to talk about gravitational waves and black holes. So the extraordinary event which happened on September 14th, 2015, two interferometric detectors detected these gravitational waves, and Gabriela Gonzalez is going to make a presentation on these two detectors. They're two extraordinary tubes where light circulates in two different areas in the United States of America. So in the length of the arms of the interferometers fluctuate for a few seconds, fractions of seconds, and here you see the raw data of the fluctuations. So 10 minus power to the power minus 18. It's not this gravitational wave. It's 1,000 times smaller than what you see here. So the question remains, how can we find in all this noise, because the noise makes this arms move, a signal which is even smaller. So the story I'm going to tell you in theoretical terms is the theory which allowed us to start off from this noise and to see 1 billion years ago the coalescence of two black holes with masses which are 30 times that of the sun and very little rotation. So what is the path which was taken to understand all this? So our story starts in November 1915 during the First World War, when Einstein, and in particular on 25th November 1915, wrote an article, The Equations of the Field of Gravitation, including the equations which define the theory of general relativity. Here you see the calculations carried out by Einstein in Zurich when he was in Switzerland in 1912, which was the start of the theory of general relativity. Just to give you an idea of the atmosphere in which he was working, so the First World War was a lethal war, and Einstein was a pacifist, and he was surrounded by colleagues who were very patriotic indeed. Max Planck signed an article stating that what were the Belgians complaining about? They were the ones that had attacked the Prussian army, and other colleagues, his friend Fritz Haber, they used to play chamber music together and invented terrible chemical weapons that killed so many French soldiers. So Einstein thought he was living with madmen, and he focused on research on a new vision of time and space. At the end of November 1915, enabled him to discover this new theory on gravitation. He sent the results of his theory to a colleague of his, Schwartzel Shield, who was an officer on the Eastern Front. There was nothing new on the Eastern Front at the time. The war was not raging at the time, and Schwartzel Shield, at the 15 days' time, came up with the first exact solution of Einstein's equations, the black hole of Schwartzel Shield. So 2 weeks after the discovery of Einstein's equations, the black hole, to a certain extent, but we'll go into further details, was discovered. And a couple of months later, in June 1916, with a mistake which was corrected in 1918, Einstein started his first calculations and work on gravitational waves. So 100 years before LIGO's observation, the stage was set with the theory, the black holes, and gravitational waves. I'm not going to frighten you by giving you too many equations, just like to remind you of the fundamental concepts which are the very basis of this Einstein's theory. The first concept is space-time. It's a concept, even it's become crystallized thanks to Einstein's theories. It's based on precursor mathematical concepts of Henri Poincaré, and is also based on the work of Hermann Minkowski. The basic idea is that, unlike what is taught at school, where we are told that things happen at all time in space. So if I take the space of this stage and I use it as a billiards table and get blue balls and a red ball to move from one point in time, they move towards one another and then carom at the center of the table and go to the other end of the table. These are impressions of space with these billiard balls, and the concept of space-time is a concept whereby you stack up all these stages of what's happening in time, like playing cards, which is stacked, and you get in vertical line you have time, and you have an additional dimension for space. So Einstein, Poincaré and Minkowski explains that we have to think of a reality not as space plus time, but space linked to time. There are structures of light propagation, and we'll come back to that within this space-time area. This is what's important for the theory of restricted relativity in 1915, where space-time are well organized, everything is calm, everything's happening at the same time, left, right, in the past and future. And then the new theory of general relativity, Einstein's new theory, which was developed to a large extent in Switzerland because the first inkling came to him in Bern in 1907, and then he started calculating these theories in Zurich in 1912, but then he went to Berlin, and that's where he concluded his theory. And here you have a deformed vision of a space-time block, which is transformed by the existence of lines, the existence of matter, energy in space-time area. This deforms these shapes, and this is explained by Einstein's equations. We're not going to use them. That's the equations you have here. And then I'm going to try, like Dali, who tried to intuitively explain this theory of Einstein's. And you're familiar with this painting. There are several variations of the limp clocks. And this is something Dali called the camembert of time and space. So the time has become limp, is not exact exactly what's happening, but let's try and use a similar analogy to explain in a single sentence what Einstein's theory on space-time is all about, which is usually curved. Now, this sentence, which sums up the Einstein's theory, space-time is an elastic structure that is deformed by the presence in its midst of mass energy. So what's essential here is you have to imagine that space between two people in this room, we think it's empty, is a vacuum. This space is a bit like jelly, as this fantastic dessert of our Anglo-Saxon neighbours you can perhaps also enjoy in Geneva. So it's jelly with its elastic properties. So what does this mean? It's an analogy, but what does it mean? It doesn't really explain what's happening. Let's try and explain elasticity in space-time. We've all learnt the rules of geometry which go back to the ancient Greeks, and an essential theorem which goes back to Thales. If I have a triangle, so if I have 3 points in space, between these 3 points I draw the straightest of lines. This triangle will have 3 angles. In A will have angle A, and at B will have angle B, and C, which are always equal to 180 degrees. So these are the laws of Euclidean geometry. So Einstein says, yes, if there is no matter around it, but if within the center of the triangle you put a ball of matter which fills the triangle, well, then this equation no longer holds, and the sum of the angles, according to Einstein, is greater than 180 degrees. It's a quantity which will depend on the mass of the ball, of constant g, gravitation, and the inverse of the light squared. So you use a bowl and you can calculate with its mass its radius. And this means that the sum of the angles around the ball will be more. So there's another effect, is that time is going to pass differently using a different mathematical formula together, the same quantity. So this quantity, this deformation, if the sum of the angles is above 180 degrees, it should have become known even to the ancient Greeks. But if you use a bowl, perhaps you'll see a slight change. If you look at a triangle around the Earth, you'll see that the changes are very slight indeed. But if we're dealing with black holes, the differences are far more marked. So you have to take enormous objects to see the changes. So what is a gravitational wave? When you've thought of the plasticity and the deformation of space, like any elastic area, if I deform the space, this deformation is going to propagate. As so it's a propagational wave of the jelly space at the speed of light. According to Einstein's theory, these waves will propagate from the point where something is happening, because matter is moving at the speed of light in all directions. And the first calculations, analytical calculations based on Einstein's theory, that showed this and calculated the intensity of gravitational waves of two objects that are moving, and the correct version was published in 1918. As of 1918, in the equations of theory, there was something that we could say that's what we're talking about, gravitational waves. How come we needed so much time to understand that they did exist and that they could be detected? Well, there were subtleties which were difficult to understand, but I'd like to pay tribute to Joe Weber. He was the first to believe that these gravitational waves did exist because he could imagine a physical object that would detect them. An electromagnetic detector was able to prove that electromagnetic waves existed. He was the first one to have the idea that gravitational waves could be detected with this huge cylinder, that they would deform the geometry and the total length of the cylinder and get it to vibrate once the wave had gone past by a fraction of quantity. That's the variation of the length of the cylinder divided by the cylinder, where there's no elastic force in the cylinder, which is proportionate to the gravitational wave. And when it gravitational waves passes, it deforms the lengths perpendicular to the direction of the gravitational wave. So the human being is going to be stretched in one area and compressed in another area. So it's only in the 1955, that's how much time we needed to convince ourselves that this was something real that was happening, that could be detected. Gabriela Gonzalez is going to go into details, and all sorts of developments had to take place is to be able to build these detectors sensitive enough to detect these gravitational waves, and interferometers were very, very useful, developed by two Russian scientists, Gertenstein and Rustovolt, and also assisted by others. I'm not going to go into detail. So although the LIGO observations were the first observations of the effect of gravitational waves on the Earth, which change the distances of an object on the Earth, thanks to discovery of binary pulses, thanks to Hulse and Taylor, we already had a proof, a direct proof of gravity propagating at the speed of light. And quantitatively speaking, this had already been tested in depth, this theory of Einstein, which allows us to predict the shape of gravitational waves because it's been tested elsewhere, so we're entitled to use it scientifically speaking.
Now let's come back to our saga of black holes. I said in December 1915, Carl Schwartzel, this is something quite extraordinary. The inventor of the black holes was called himself Schwartzel Shield, which means black shield. So he wrote down this formula in December 1915, a formula which seems quite simple, but this equation contains the concept of black holes in a rather cryptical way. And 50 years of research and development and theoretical and experimental development were needed to understand that there was a physical object behind it and an object that existed in nature. I'm projecting here pictures of very important people in this regard, Oppenheimer in particular, and also the New Zealander Roy Carr, who found a solution of this equation for a black hole rotating around itself. Don't be afraid, I'm not going to read out all this. Just want to tell you that 50 years of discovery were needed in astrophysics, in observation, and new theoretical ideas to understand that a black hole was something quite real. Because we first had to understand that stars are developing. They are born and then they die, and something happens with dying or dead stars, leading to neutron stars and then leading to a black hole. All this led to an essential article by Oppenheimer and Snyder in 1939. And even then, you have to wait until the discovery of pulsars and then quasars and other elements before you could get a clear picture of everything. Not everything is included in Schwarzschild's work. Not everything has been understood from the start on the basis of his equation. Now let's try and explain and describe what is a black hole after all. a first approximation of a black hole tends to lead to the following definition. It's a very dense object, so dense that if you want to throw it, of course, if you want to throw something up, it's going to fall back. But if you throw it at a speed of 11 kilometers a second, then it's going never to fall back on Earth. As soon as the speed at which you throw something up is higher than the speed of light, then no light can be emitted. So this is one definition of the black hole. But the black hole, as understood by Snyder and Oppenheimer in 1939, and in particular by three Russians, Zalkovich and Delkov in 1965, with essential mathematical contributions by Penrose and others in 1969. I'm going to explain to you this sketch, this diagram here. You remember that I talked to you about space-time, which was kind of stacking up of playing cards. In this picture, the vertical dimension is time. If you take sections, then you have what happens in the space. The first, I cancel one dimension of space. This is no longer a sphere, but it is a disk. This star is dying, has run out of nuclear matter. There is no source of pressure compressing it together, and therefore gravitation tends to lead to the star collapsing on itself. This is going to happen a few moments later. As you see, the disk is smaller, which means that the star is collapsing. A collapsing star would, in theory, collapse until all matter has condensed at one point in the middle. So you think everything is going to happen at that point. But there are other things happening as well. The first gray areas and the more black area mean something on this diagram. If you emit a light flash, generally speaking, this flash of light will go in all directions at the speed of light. But because of the collapsing of the star, the light starts leaving the star, but becomes finally stops leaving the star. And this part of the diagram represents the future of this sphere of light with a constant radius. That means that this sphere of light tries to escape the star but stays put. Just like if you have a bathroom and you fill your bath with water, and there is an insect at the surface of the water which tries to escape. If the speed at which the water is going out is higher than the speed of the insect, then the insect cannot escape. This is the case in this black hole. The space jelly has become so elastic that it has become actually fluid, and everything collapses towards the center. The definition of a black hole is a sphere of light that stays put. At the center, you should have the concentration of all matter, but it seems, and we'll probably talk to that later on, it seems that at the center of the black hole, there is no elasticity of space-time any longer. It's as if you had ripped up this jelly. There is no space-time beyond this limit. When people understood that Schwarzschild's solution included all this, they needed a lot of other contributions before they were able to understand that. There was another contribution on which I want to insist. It's the contribution by Freeman Dyson. Freeman Dyson was the first one in 1963 to solve an exercise in a famous article The exercise was the following one. Take a system with two objects, two stars and two dying or two dead stars, two neutron stars, extremely dense stars, rotating around each other. If you use a formula due to Newton, two bodies rotating around each other have a certain energy, a potential and a real energy. This energy is going to be constant. But as a matter of fact, it's diminishing because, according to Einstein, this system emits gravitational waves. And Einstein had already calculated what was the flux, the loss of energy ad infinitum. If there is a loss of energy, it means that this energy is dissipating over time. So this equation gives you the solution. And the aim of the exercise was the effect is so small that you can forget it. For 50 years, people knew that gravitational waves existed, but they thought that the effect was negligible. Well, Dyson was the first one to say, yes, it is true. At any point in time, it is a very small effect. But if I'm waiting for 100 and 500 million years, as long as needed, these two objects are going to get closer to each other. Their gravitational waves are going to resemble a sinus wave. Their frequency will increase, and in the end, there will be an apocalyptical flash of gravitational waves emitted once these two objects melt or fuse with each other. And Dyson gave us as channeled, is it possible to calculate that flash of light? And he said, in any case, it's going to be very interesting to think about it. That he said in 1963. I'm not going to enter into the theory that enabled us to calculate very precisely the formula about these two bodies rotating around each other. Many, many works so research was needed for that. But towards the year 2000, in particular, in articles published by Alexandra Bonamour and others, we were able to calculate the gravitational wave, the space transformation wave that enabled to enabled us to reach the point where these two objects melt or fuse with each other. These calculations were made on paper, actually, or in the mind, and 5 years later it was able to use a computer to calculate the same thing. Actually, 30 years were needed for people to use computers with Einstein's equations to reach a result. Everything was based on very old mathematical works made by French mathematicians. The first comparison between numerical and human calculations led to a very good consistency. And the end result was that we now have a method by which we can calculate the movement, the relative movement of these two black holes rotating around each other. And over this time, you see the gravitational wave. These two black holes are progressively distorting the space around them, the jelly around them, like when you stir your soup. And this, at the beginning, these two black holes are rotating very slowly around each other, so the period of the wave is rather regular, and then it becomes increasingly faster, and then up to half of the speed of light. And in the end, you have this final phase where two black holes fuse or merge into each other. With this new method, improved by computers, you can calculate or predict the gravitational wave. You can predict what will be the deformation or the distortion of space-time in all directions, because these waves are spreading in all directions at the speed of light. This is a process that takes billions of years, and over these billions of years, these two objects are rotating around each other, and then in the last few seconds, the last orbits are being registered, and both black holes are merging with each other. You can imagine two soap bubbles that, coming closer to each other, melt as soon as they touch each other in order to create one big bubble. Same thing for black holes. You'll get, in the end, a huge black hole, which is going to revolve around each other because it is keeping the kinetic movement. But there is no equilibrium. There is no proper shape to this black hole, and will go on vibrating like an object which is not yet in equilibrium. This object will emit waves until it reaches an equilibrium stage. That was already calculated in the 1970s. And then in the end, you'll get only one black hole, which is at an equilibrium stage. It's quite impressive to think that this event at the time of the fusion of these two black holes is emitting a power in watt, or like what you pay for your electricity grid. This power is 10 times higher than the luminosity of all stars of all galaxies in the whole universe. You have the luminosity of the sun. There are 100 billion suns in our galaxy, 100 billion galaxies, and you can even multiply that by 10 to reach the luminosity emitted in form of gravitational waves by a black hole, even if this is not visible because it is only a vibration of space. It is quite impressive. A few words now about these detectors for gravitational waves, LIGO. Gabriela will explain that to us later on in the week. You have these tubes and also the Virgo French-Italian detector, which enabled detecting fusions of or mergers of two black holes. So you have huge vacuum tubes, 4 kilometers long, where you have light circulating between mirrors. And this gives you a very sensitive receptor calculating the variations of distance, thanks to the properties of the interferometric detector. These are the raw data of the variation of the length of the arms of these tubes during the first event in September 2015. What you see actually is the gravitational wave signal, which is this signal emitted by two black holes, 10,000 times smaller than the amplitude that you can see here. In other words, it's impossible to see it in the noise that is surrounding it. So you have to extract it from the noise. What is also impressive is that the physical movement of these arms of the tubes corresponds to 1 billionth part of the size of an atom. This energy that has been emitted 1 billion years ago becomes 1 billionth time the length of these tubes, the dimension of an atom in these tubes. In other words, it's close to zero. However, what is wonderful is that these experimental work and detections by LIGO and Virgo enabled us to detect them. In order to understand this signal, you need a specific technique of a filter, a special filter, in order to filter out the signal from the noise. If you know nothing about the signal, you can't find it in the noise. However, if you know what shape this signal might have, you can look for it in the noise by a mathematical technique called convolution. Alexandra Bonanno used the technique that had been created and calculated for LIGO Virgo 200,000 possible signals for gravitational waves according to the various possible masses of black holes, and this gave us a databases through which we were able to detect all these signals that have been detected later on for the analysis of data. Several events of coalescence of binary black holes have been detected with various masses. Here you see 30 times the size of the sun, etc. Now, without entering into details, let me explain why this was the first direct proof of the existence of black holes. First of all, this diagram, which is in the article about LIGO, is both essential and correct, but a little bit leads to misunderstandings, because in order to filter out the noise, this leads us to believe that the essential part of the signal is the signal at the time of the coalescence. Because let me remind you, the shape that was foreseen with a gravitational wave that increases and is at its highest point at the time of the fusion of these two black holes. So you get the impression that this is the point in time where both black holes are coalescing. But as a matter of fact, if you ask yourselves what is the amount of information that you can extract from this filter, you get this curve here giving you the quantity of signal at each stage of the frequency. And the most important part of the signal-noise ratio here is obtained here at a frequency that is about 50 hertz, much longer before the fusion of two black holes as such. So the essential of what LIGO saw is not the fusion of these two black holes, but the last movements of these two black holes, which enables us to extract the calculation of the mass. But the fusion does take place indeed, and this part is also extremely important. It's a weaker signal, of course, but it's still important enough to confirm that if you can decompose this signal into two, you have the possibility of testing the fact that the signal is compatible with the masses or the elements that you've extracted before. This is explained by this diagram, which I'm not going to explain in details, but it shows that there are two parts, a part directly linked to the fusion and a part linked to the time before the fusion, which is the proof that you have indeed seen the fusion of two fusions. You've used Einstein's theory, but in two different parts. Now, let me say a few things about black holes in astrophysics. You've heard about black holes much longer, or a long time ago. We've read about them in newspapers for a long time, because astrophysicians were convinced that there were in our galaxy sources of stars, or two stars, dead stars rotating around each other, and obviously there must have been a black hole somewhere. Many people were convinced that at the center of any active galaxy there are huge black holes. Rainer Genzel and others are convinced that at the center of our galaxy, where we can't see much at the time, there are stars rotating on very far away orbits, but that enables us to be more or less convinced that there is a huge mass 4 million times as higher as the mass of the Sun at the center of our galaxy. What could it be except a black hole? So there were many indirect proofs of the existence of black holes, but LIGO was the first time where we could see a signal directly linked to the fusion of two black holes. Another very remarkable event was that on the 17th of August 2017, LIGO and Virgo together were able to see the element that Dyson was mentioning. In other words, the fusion of two neutron stars. Two neutron stars are only 1.5 times the mass of the Sun. But this system was rather close to us, so emitted a signal that used the spiral movement. There are millions or thousands of cycles of these two stars gravitating around each other. What is absolutely amazing about this is that this event was followed by the observation of kind of bursts of gamma rays and other electromagnetic signals. And all this showed that the fusion of these two neutron stars created a very violent astrophysical event with emitting gravitational waves of all the spectrum. That was the beginning of the multi-messenger astronomy. studying not only gravitational waves, which is wonderful, but also limitating, but also integrating another event with electromagnetic waves. This will also be rather pertinent for Claudia de Ram's intervention. I have to mention that this observation, the fact that the electromagnetic wave has been seen 2 seconds after the end of the gravitational wave, shows that electromagnetic waves, light in other words, is propagating at the same speed as the gravitational wave, just like Einstein's theory predicted. And you can see that experimentally there with a precision at the 15th decimal. So you can show that the difference between the speed of propagation of gravitational waves and electromagnetic waves is smaller than 10 to the minus 16. So you can use Einstein's theories on other theories as well. Now let's turn our eyes towards the future. On the basis of a Polish research group, it's possible to think that in a very near future, once the new detectors will be launched, it will be possible to see 3 times further away from us, and therefore 27 times more events. So you'll probably see one coalescence of 2 black holes every day, and in the future you'll see one coalescence of 2 black holes every 5 minutes, as soon as we'll have the possibility of detecting them. We hope that gravitational waves will lead to something more mysterious even than black holes. For example, strings, a cosmological background, and gravitational waves in space, etc., etc. I'm not going to spend a long time on this, but this was I mentioned black holes theory as if we understood everything. Mathematically, more or less everything has been proven and explained, but actually there are a few open mathematical questions. Let me conclude with quantic proprieties of black holes. As Thierry said earlier on, the problem today is to unify our traditional theories with quantum theory. A very important discovery was made in the 1970s by a young Mexican or person who was born in Mexico, Jakob Bekenstein, and Stephen Hawking. Stephen Hawking wanted to demonstrate that what Bekenstein said was completely wrong. His idea was, since a black hole is something that emits nothing, if you have hot tea that you throw into it, you're going to lose the heat that is in the water of the tea. And in physics, this heat is linked to disorder. So you've lost disorder. It is as if you had gained order. But the second law of thermodynamics thinks that disorder is always increasing. So Bekenstein says you have to associate a black hole with a kind of quantity of entropy and a loss of information. And Stephen Hawking was the first one to calculate this entropy and to calculate the temperature of a black hole. As he said later on, a black hole is heated extremely highly at an extremely high temperature. If a black hole evaporates because it is so much heated, his mass is going to decrease, and in the end there'll be no black hole left. So you've transformed the initial state that was a very pure quantum state into something that is heat, which is impossible according to quantum mechanics laws. So there is still something that we do not understand there, and maybe Andrew Strominger is going to mention that on Friday. Now let's turn to the conclusions. First conclusion is, I gave you 2 examples of black holes and gravitational waves where equations, the solution to equations, was more intelligent than the physicists themselves. You needed to wait for 50 years to understand that it was something quite tangible behind it, whereas our human mind still has difficulties assimilating and understanding all this. Otherwise, in 2015, for the first time, we were able to see this jelly move with gravitational waves, and this gave us a direct proof of black holes. Theory was extremely important in this regard. And finally, for my last conclusion, if you want to go beyond my speech tonight, you can be fascinated by modern physics and think this is a quantum cosmos with a super stacking of different realities one over the other. But why is all this important? If you listen to a CD, or if you exchange data with your smartphone, or if you make a test that uses the electron positron annihilation, or if you use your GPS in your car, everything comes from the general theory of relativity. So the applications of theoretical physics is in our everyday life. But the danger is that you reduce science to all this only, and you forget about the philosophical beauty of all these thinking. And this is why, and this is also one of the aims of the Wright Foundation, please fight against what Snow called the divorce between two cultures, the scientific and the popular culture. I'm sorry, I did something wrong here. Here we are. I'd like to go with Schrödinger and say that science has to be considered as an integral part of humanism. And Einstein, he will be the last one to have the word here, you have to take seriously the consequences of science, the philosophical consequences of science, even if it seems absurd. For example, the scientific consequences of the theory of relativity is that passing of time is an illusion. And a philosophical consequence of quantum physics, which is also discussed in this cartoon that was mentioned, is that our reality here is much more complex and is a kind of stacking up of different realities that are, as a matter of fact, incompatible with each other. However, quantum physics tells us this is reality. You have to change your way of thinking about reality and not be content with what you learned at school or what you believed or what mankind believed for the last thousands of years. This audacity in thinking differently is something that is directly derived from all these equations. So please think philosophically about all these consequences.
Merci. Merci beaucoup Thibault Damour pour ce fascinant.
Thank you very much, Thibault Damour, for this extraordinary travel trip into black holes. So we're going to have a general discussion in English, and you can put your questions in two ways. Either grab a microphone, which will be brought to you by a hostess in the room, or by Twitter with hashtag Colloque Wright. So you can put your questions by Twitter and they will be given to our speakers this evening. Now we have several speakers on the set. We have two additional speakers who are going to make presentations.
What I said before, the discussion will be held in English. Please ask your question either live with the two microphones that are in the room or through Twitter. The hashtag is there, so just use the hashtag and ask your questions, and they will be relayed to the speakers here on stage. So now I have the great pleasure to welcome on stage as well as tonight Andrea Accomazzo and Gabriela Gonzalez. Gabriela. So, welcome to you both. We'll hear from you tomorrow and Thursday, right? I'll start with you, Gabriela. So you were strongly involved in the discovery of the gravitational wave. So I presume we will expect your call on Thursday to talk about this. But in a few words, just tell us about that moment when you realized that you had exactly the signal that Thibault showed on the screen, that you saw it and you said, okay, that's really it.
Well,
should be okay.
I have to say that it wasn't one moment. The moment where we saw that some of the early indications that there was a strong signal in there, we didn't believe it. It took us actually a whole day to convince ourselves that we had not created, we had not simulated, that this was not a simulation, that it was data in the detector. But it was so strange. I mean, Professor Damour mentioned that it was a signal that seemed to be produced by black holes that were larger than any ones that had been seen in X-rays, that we just had to be sure. And it took us months using simulations, using these waveforms to match them to the data to convince ourselves that this was not an artifact. So it wasn't one moment. It was months of work to make sure that it was there.
Andrea Comazzo, you also work in the space sector, but in a kind of different space sector, if I can say that, because your task, your job, is to bring spacecrafts to planets or comets. Planets, planets. We saw 2 weeks ago the launch of Bepi Colombo to Mercury, and comets 4 years ago to the comet Chury, let's call it Chury or Churyumov of Gerasimenko. So do you see any parallel with what you're doing and what they are doing?
Well, to see parallels is pretty difficult. The first thing I would say is I'm still very happy to work with F equal ma compared to all these equations. And the second thing I've learned today that is my brain is not as elastic as a jelly. Actually, it's far less elastic than space-time. I find some. No, of course I don't have a parallels, but of course we are very pleased to fly missions that might help also in this direction. We are. The agency is preparing the LISA mission. This is the intention actually to fly such a mission, which is actually designed to detect gravitational waves in space. So this is something we are doing. Just to give you an information, we also have to take into account relativity in the job we do. For example, when we flew Rosetta and where we fly our interplanetary missions, I'm not expert in this specific domain, but for example, we cannot use the time we use because we have relativistic effects. So we use actually the time of the barycenter of the solar system, which is not the time we use here on the Earth. It's slightly different and evolves differently because of relativistic effects. So we have to take this into account. So we have proved as well that we have to live with these effects.
And maybe in terms of technological challenges, because I presume that for both of you, you had tremendous technological challenges to overcome.
Well, it might look odd, but one of the biggest challenges you have in space business, in particular to the job I do, which is flying spacecraft interplanetary, is measuring of time. Because everything is based on time, and measuring time properly on ground when we detect our events on our spacecraft is fundamental. Everything is linked and depends on measuring time.
Time is just an illusion, we've heard, right?
Indeed. Now I will have to rethink of what we are doing at home.
And what about the technological challenges in LIGO?
Yes, actually, for us, it's not as much measuring time. Of course, we have to use atomic clocks, but GPS time is actually good enough for our experiment. It's measuring space. It's measuring the distances between mirrors, like Professor Damour said. The distance between these mirrors at 4 kilometers away moved by the gravitational wave less than 1,000th of a proton, less than a billionth of an atom. So making the mirrors not move more than that by other sources, like the ground moving or trucks driving.
The waves, I've heard that the waves do influence the waves.
The ocean waves, right? The surf waves on the ocean, which is relatively close to Livingston, Louisiana, but not so close to Hanford, Washington. But surf waves on the coast produce all over the world waves on Earth that have about a micron motion at much lower frequencies, but we still have to counteract that to make our mirrors not move as much. So this has taken decades of technology development to suspend mirrors from pendulums in vacuum 4 kilometers away so quietly that we could measure not just once, the first one in 2015, but since then, several gravitational waves.
Let's come back to the black holes. Actually, I was amazed to learn that, he has a mic, to learn that there was no proof until very recently that, or still now, that there is a black hole at the center of our galaxy. And just actually last week or 2 weeks ago, a team at the ESO, that's the European Southern Observatory in Chile, showed that some, let's call it stuff, was moving at 30% of the speed of light close to the center of the galaxy, which could be a first hint of the presence of this black hole. So is that correct? And what does that mean? What's the importance of that discovery?
Yes, indeed. So for years, the study of those stars going around has suggested that you needed to have 4 million times the mass of the sun concentrated in such a small volume that it was difficult to imagine that it could be else than a black hole, but it was not a proof that there was really a black hole there, although they had a good test of general relativity recently. And this recent experimental fact that they seem to, although they are very careful, seeing a hot spot in which could be of the accreting material falling into, going around at a third of the velocity of light and then falling into the black hole, it's indeed one of the first hints that they are going to be able to see the structure very near the black hole and prove, if this is confirmed, that this has to be a black hole. And in a few months, other experiments of this type, I mean the so-called Horizon telescope, should see maybe the silhouette of really the stuff around the black hole.
So that's the picture of the black hole. So it's strange to talk of a picture of a black hole, right? Is that something like in Interstellar? You remember the movie? Do we have to imagine it, this way?
I like to call it the silhouette. No, it's something against. Well, a silhouette is what is the shape of an object when you are against a background light. So here you need to have a source of light around, which is the stuff which is falling in the black hole and creating light. And then you see something like a black region, a shadow or a silhouette. And then, although probably it will be noisy, I mean, they will not see very precisely what is computed because you don't know the complicated physics of the material falling into the black hole. But it's very exciting that they will see that in the coming months. They will announce results for the black hole at the center of the galaxy and also for a black hole 1,000 times bigger and 1,000 times farther away in M87. And that would be extremely exciting to see this.
What about waves? I mean, is there a chance that we see gravitational waves from our black hole? Let's call it this way.
Well, we'd like to, but gravitational waves produced in our galaxy do not happen as often of the kind that we have detected, happen only once every 10,000 years. So even though we would very much like to see those because they would be very strong, they're not likely to happen. However, things falling into the black hole or mergers of black holes at the center of galaxies could be seen and will be seen by the LISA project, this space interferometer that will be flown by the European Space Agency. We have to be a bit patient because the launch date is 2034, but we have been patient and it has paid off, so this will happen too.
Will you be there for the launch? Will you drive it to space?
Well, I just want to say that the Rosetta mission was conceived in around 1985, was approved in 93, launched in 2004, and arrived in 2014. Was 30 years, so we're not that far from launching LISA. I hope to be retired by that time and be skiing in the Alps.
Yeah. Let's stay with the ESO telescope. Actually, it was one very precise instrument at the ESO site in Chile that discovered this silhouette of the black hole. But a few months ago, that was in July, I think, they discovered something else. And this was a star passing by this same black hole called Sagittarius A. And actually, scientists were expecting to see really tiny variation of the Einstein theory, right? But they didn't, which showed again that Einstein was right. So were you kind of disappointed that there was no hidden physics behind this?
You did not expect to see deviation of Einstein's theory. So what they measured is the displacements toward the right, the so-called redshift of the light emitted by this star when it was going quite close at the periastron of this black hole. And this effect has been tested with much better accuracy in binary pulsars and also in the solar system. So there was no strong hint that it should be wrong for this case. You do think that probably Einstein theory is not the ultimate word on gravity, and there is the issue, what is the best place to see possible deviations? One space mission which is now testing general relativity in an interesting regime is the microscope mission, which is going back to the basics of gravity. The basics of gravity, as discovered by Galileo 300 years ago, is that if I let bodies of different composition, like a ball of marble and a ball of iron or copper or whatever, they, independently of their mass, or even if they have the same mass but a different composition, they fall in exactly the same way, Galileo said, although the story is more complicated than that. And Einstein realized that this was a remarkable property that did not need to be exact, but he postulated it as being exact, and he created a theory on it. But the recent, the development of physics in the last century has suggested that maybe it is a fragile property. And when you have extensions beyond GR, you very quickly violate this property. Alas, again, the microscope mission has published not yet the final results, only the mid-mission results. And now they have confirmed that all bodies fall in the same way to 1 part in 10 to the 14, which is a big improvement compared to before. And I would have liked, and with Gabriele Veneziano here, for instance, we had hoped that the prediction from string theory, the dilaton, could have shown up as a deviation in this experiment, but he has not yet shown up. But we keep the hope of seeing something one day.
So Einstein is still right.
Einstein is still there, yeah.
So I think it's now a good time to open the room for questions. Unfortunately, I don't see the room because of the light. So there is one here at the forefront, and one here in the middle. Yes, and one there. So 1, 2, 3. First row.
Thank you. Just a question about the 2 neutron stars that coalesced and made the gamma rays and the gravitational waves. I remember reading things about the gravitational waves and the gamma rays. There was like a 2-second lapse in between those 2 events. How come, if they travel at the same time, why did you, the scientists, see those 2 seconds in between those 2 events?
Gabriela?
I have to say that the first thing we all thought is that after traveling 130 million light years, arriving with only 2 seconds of difference was amazing. But the answer to your question is that the gamma rays are produced after the neutron star merge, and the gravitational wave the time that we measured with the gravitational wave is the time of coalescence. The time measured by the gamma rays is the time those gamma rays were produced. And in fact, there were 2 experiments, 2 satellites, Fermi and Integral, that measured gamma rays, and they measured it at slightly different energies, and the rays at different energies came at different times. So the gamma rays are telling us about what happened at the merger with electromagnetic waves produced. The other electromagnetic waves, well, the visible ones, the ones in the visible, we don't know when they were produced because they could only be seen at night, several hours later. But the X-rays and radio waves emitted by the same system arrived 10 days later. So the merger, the structure that happens after the merger is very complicated, and astronomers, astrophysicists are still analyzing the data.
Still, one should say that actually nobody had predicted why 2 seconds. And there is no model saying why 2, not 10 seconds, or okay, it could be 1 minute maybe. So finally, it's not so, I mean.
Yes, it's still, to me, who I am not an astrophysicist, to me, the fact that it is 2 seconds, it's amazing. But if it had been 10 seconds, I don't think people would have been surprised.
There was one question right here. You have the mic.
Okay, I would like to know, please, if, let's say, we could survive just very close to the fusion of 2 very big black holes, and we only have the effect of the gravitational wave. Could you just tell us what would it be to have big gravitational wave arriving toward us?
The effect is actually quite small. It's even quite near when the waves are formed in the wave zone. It's less than 1% of fluctuation of the distance between the molecules in your body. So it's not, by the way, it's interesting to remember that there is a beautiful book by Gamow in which he represents the arrival of a gravitational wave on a beach with extreme effects, like he's seeing his fiancée being distorted and disappearing and things like that. So there are no gravitational waves which are that strong, and the reason is that this jelly of space is extremely rigid, actually. Space is elastic, but the elasticity is nearly 0. That's why a medium which is so rigid, waves propagate very fast because they propagate the velocity of light. So we knew that space has to be very rigid, okay? And it is extremely rigid. It's difficult to create big gravitational waves.
Your brain is probably more flexible than that.
There was one question here. Yes? Yeah, fourth row.
So I had a question about the gravitational waves, really the detecting of it, because you rely on filtering. So in fact, you find what you're searching for. And I was wondering, is maybe there is another cool system, I don't know, maybe I really don't have a clue, but which is also has a nice waveform, which could be kind of also a candidate to find it. Are you searching for something like that?
Yes, we are searching for, well, I couldn't say everything, but we search for many, many more things than coalescences of binary systems, for which we have very good models, thanks to waveforms like Professor Damour mentioned. We do have methods that look for the unknown, that do not rely on any model for the gravitational wave. They only look for correlations between the data in the 2 detectors. Of course, they are less sensitive, so you can only detect things that are very strong. And with this method, this first gravitational wave was also detected. The other gravitational waves that were mentioned, also produced by the merger of black holes, those we have only detected because we look for those waveforms, or for similar waveforms. We have to test with many, many waveforms to deduce what mass or what were the properties of the system. But we look for gravitational waves of the unknown. Unfortunately, and I say unfortunately because I think they would be the most exciting ones, we have not found any of those. We also look for periodic waves that would be produced by rotating stars, like rotating neutron stars, and we also look for rumble, for a stochastic noise that would have been produced by the early universe, although probably with an amplitude that we are not sensitive to, or perhaps by many other signals mixed with each other.
I think we have some questions on Twitter first.
Yes, we do actually. We have one double question and one multiple one. So let me start with the double one, which says, well, if gravitational waves travel with the speed of light, it means that there is no refractive index for gravitational waves. That's the first part of the double question. And the second part is to say, well, but the light should also follow curved paths to come to us. So actually, shouldn't we be very surprised that both arrive at the same time?
Yeah, that's a very good question. It's true that light usually does not travel at the velocity of light because of index, because of interaction with matter. It is slowed down. So you need to have a transparent enough universe, or maybe the 2 seconds are also part of the index linked to that. And the other part of the question is that actually there exists a kind of index of refraction in the sense that when we say that gravitational waves propagate at the velocity of light, it means they surf on the curved space-time. I mean, space is deformed, and they both travel at the local velocity of light, and as we have seen around a black hole, the local velocity of light is quite different from what it is, but both light and gravitation, if we can neglect plasma effects, if we can neglect index due to the matter being around, they will surf along the curvature of space-time and be delayed in the same way, like cosmologically.
The multiple question is looks a bit like that. How should we look at black holes in alternative gravitational theories to the theory of Einstein? And the person asking the question speaks of negative masses and of a theory of Jean-Pierre Petit, but I think you can probably try to take it in a bit more general way than just that. I mean, what's the place of black holes in alternative gravitational theories?
That's a very good question, and maybe Claudia Doram will talk more about this. Although now there is very good evidence from many different experimental tests of the validity of Einstein theory, it is very important to always keep our mind open and try to interpret data in terms of limits on a possible modification of Einstein theory. And a black hole is such an extreme object in Einstein theory that immediately when you modify Einstein theory, you ask the question, are there black holes? What are the properties of black holes? Actually, it's a very tricky question because in most alternative theories, the black holes are the same. It's difficult to have a good theory which had good field theory properties and which have black holes different from Einstein's theory. Black holes tend to be the same in all good theories of gravity. But it would be interesting to anyway do phenomenological tests of whether the black holes we see are fully compatible with Einstein's general relativity predictions.
In the meantime, there's another one that came, and which says, we hope to understand the cosmic microwave background better, knowing of the existence of gravitational waves.
So what's the question exactly?
Well, I guess the question actually deals with the polarization of the microwave background. I guess that's what's being pointed out. It's not there, but that's what's to be expected.
Yes, I'm not an expert on that, but indeed it would be very important to see via polarization effects. I mean, if the ratio of the so-called tensor gravitational wave components in the origin of the CMB fluctuation is not too small, we should be able to see very early gravitational waves, and what is even more important is that these very early gravitational waves would be quantum in nature, and that would be a direct observational test of quantum gravity. I mean, the quantum fluctuations of the gravitational field produced in the early universe. So for the moment, the presence of dust in the data has not allowed us to see that, but it would be very exciting in the future to be able to see this.
All the more so since it would be a signature of the inflation period at the very early
yes,
universe.
Even more early than, I mean, a more direct handle on the origin of inflation. Yeah.
Thank you. Is there more question in the room? There was just behind you, Thierry. Yeah. Here and here one. Yes.
Thank you for the presentation. Actually, I have a question for Damour. As you said, the energy generated by two black holes is bigger than all the stars reunite in universe, in our galaxy, and in all universe. That's right. Yeah. But do we know the number of these stars in all universe? Because as I know it.
Yes, no, it's just a figure. The number was put there. The power in ergs per second is 10 to the 56. So to get 10 to the 56, you need, the luminosity of the sun is 10 to the 33 ergs. Then you need 11 more powers. This is like conventional one galaxy. Then you need 11 more powers, like 10 to the 11 galaxies. And you need a factor 10 more. It's just a way of counting. I'm not claiming that we know the number of stars and the number of galaxies in the visible universe within the accuracy that I'm citing. It's just a way of saying, if you take into account roughly what we know is the visible universe, it's striking that the power in watts, ergs per second, emitted during the coalescence is bigger than that. It's a fact.
Okay, so
but I should say that in the natural units that the theorists we would use to measure this, which like Freeman Dyson would consider as the natural luminosity unit for the coalescence of two black holes, the power emitted is small. It is 10 minus 3 Dysons. Okay, 10 minus 3 C5 divided by G.
So it's
both very large and very small.
Okay, so
depends on the unit.
So it's still relative. So we don't know the number of stars. So
no,
we still don't know
but the question is not relevant. It's just a way of.
And another question, just because I'm still confused about this time, being an illusion. And but if we say in black holes the time doesn't exist anymore, or it exists, but it's I don't know, it's not ending, or so. How come the black holes are ending? I mean, it's a moment till it starts, till.
What means time is an illusion is the following: if you have a twin brother, and you take your twin brother very near the surface of a black hole, while you stay here, and you stay like that for 10 years, when then you lift up your brother, it will not have aged at all. Okay. So it shows that the notion of time can be completely transformed by effects due to matter or speed if you are in special relativity. And when you think about it, it means in some cases, for instance, if you jump in a rocket which goes around the Earth very fast, you can see the future of Geneva in 65 million years. You can, in 1 minute of your time, come back in this room after having traveling around and see Geneva in 60 million years in the future. You can jump in the future. Think about it philosophically.
So we'll take two last questions here, sorry, because time is running really fast. So
does not exist, but it runs fast.
Yeah. I see two persons. So this person, yes, please do, Fanen, and Boris, you will do last.
Okay, I would like to ask Professor Damour, if by pure hypothesis there were a black hole close enough to Earth and a big black hole, what will change? I mean, we will feel it, and I will explain my question. You say that black holes somehow twist or change space-time, but if we have a black hole close enough, we will see somehow our space and time change, or it will be like the parallel worlds, we will change and we wouldn't even notice. No. And one other question was is related to this one. What does the gravitational waves tell us about the fact that the universe is infinite and keeps growing? What does it tell us about it?
These are very different questions. Okay, if you have a black hole which is not immediately coming now in this room, you will feel it like another star. I mean, you will feel the gravitational attraction. The change in the dynamics of the solar system will be modified. The trajectory of the Earth will be modified. And then if the black hole comes very fast and impinges on the Earth, then it can, if it is big enough, create violent effects like eat up part of the Earth. I mean, if it is large enough. But to see the changes in the structure of space and time in the black hole, you really have to jump in, okay? But it is not in a parallel universe. It's a classical effect. You would need quantum black holes to start discussing what it means to have superposition of realities with black holes.
Last question here, because time is running really fast. Yes.
Thank you. Keeping scientific questioning open needs sometimes to go to the farthest limits of the universe, as you have done, and sometimes it just requires reopening every day the elementary physics textbook and reading it afresh. So I will try to illustrate that. One of you mentioned F equals ma. I think that Richard Feynman said it is not a law of nature, it is half a law. And if I got it right, why he says it's half a law? Because of the 3 parameters, just one can be measured directly, A, acceleration. Unless you consider that inertial mass can be measured by a weighting machine, which is the whole issue of gravitation, which brings us to the second half law of nature, which is universal gravitation. So even reopening every day the simplest equation we were told at age 10, and which every scientist, even Nobel Prize winner, repeats sometimes without fully understanding them, is a source of scientific marvel and questioning. What is your way of bridging the marvels from the end of the universe to the marvels of reopening the elementary textbooks with a fresh eye?
Well, you want to answer? You suggested.
Well, I can obviously fully subscribe to such a statement. I'm an engineer. I'm not a physicist, so I have strong limitation in understanding all what has been discussed here. But my way of describing is everything that we say is just the way we see the universe, the way we describe it. It's just a fraction of reality. And this is a long way. And I fully agree with you that going back to some of the, let's say, the laws, the formulas we understand most, can be for inspiration, can only be for inspiration to understand much better all what is around us. But everything is just the way we describe what is around it is not reality. I think we sometimes fall into the trap that we think everything we describe is reality. No, reality is something else. We put an enormous effort to describe it, and we're obviously not there yet, because every time we find something that is missing.
So I think it's a good time to close this event. Before doing this, I'd like to do 2 things. First, to come back to Einstein, because Einstein was, at the beginning of your talk, is behind LIGO, and you also mentioned Einstein, so I'm happy that the 3 of you answered the question. But before that, another question. Actually, I'm curious, if you had Einstein in front of you at the moment, what would be the one question that you would ask him?
Are you happy? You know that Einstein, at some point when people tried to solve his equations, were spending time, said, but why do you spend so much time on equations which are just provisional? Because he was never sure of having found something solid. He always thought it's the next step which is important. He always felt there was something inadequate in his description of matter, in his description of space and time. So let's keep this spirit of openness towards the future.
Okay, I would have 2 questions, but the one I can ask maybe the colleagues here, the one I would ask Einstein is, do you agree that there's something wrong in what you say? This would give me hope if you were to agree.
And Gabriela?
I would give him a tour of LIGO, and then I would ask him to help us fighting the quantum noise, which we expect it's going to be the limiting noise in our measurements very soon.
So I'd like three of you to react to one quote of Einstein, who, like space-time, has been distorted, but the original version goes this way, was published in 1936. It's the eternal mystery of the world is its comprehensibility. The fact that it is comprehensible is a miracle, and it has been distorted or shortened to the most incomprehensible thing about the universe is that it is comprehensible. So what does that
I think
inspire you?
It's a very deep quote of Einstein, yes.
What does it say?
I mean, it says that from the humanistic point of view, we should always marvel at the possibility of the existence of science. I mean, there is no a priori reason why the poor human reason, which is a very small jelly in some of the brains, can comprehend what happened in the Big Bang, in black holes, describe it with mathematical equations which are valid up to the 15th digit. It's a marvel. So beyond that, we have to keep the capacity of marveling at the universe without over-interpreting it, but marveling at it.
To me, it also says, of course, I agree with Professor Damour, but it also says that what we comprehend of the universe, about the universe today, is less than what we will know about it tomorrow, because our comprehension is limited, but it's expanding all the time, and that excitement about how much more there is ever to comprehend, to learn about the universe, it's very exciting.
Andrew?
Well, to me, it says that if we were to stop curiosity of the human being, then we wouldn't be here today. And it's a continuous quest, it's a continuous search for something that we don't understand yet.
And maybe the very last question to you, Thibault, because that's your evening, actually. I came to you 10 years ago in Paris to do an interview for the newspaper Le Temps at the time. And you told me that you were fearing something. And what you feared was, yes, you were fearing something. I read it as it was written in the interview, that the human mind will not be able to understand the laws of the universe, which would have become too complex, speaking of the laws. So are you still afraid that we sometimes won't be able to understand what we're doing?
That's part of this marveling of Einstein. Yes, I don't know if I fear it or I stop fearing, but when you think of some of our friends, animal friends, and you think that even if you love a dog, you will never be able to explain to him what is Einstein's theory, and why can we understand? And then when you think that maybe we would be limited, that maybe we will reach a point where things will become too complex and we won't be able to continue this rational path towards the universe. That would be a bad end for theoretical physics. But we see no sign of it yet, okay?
So you're not afraid anymore?
I'm not maybe afraid anymore.
So thank you very much to the three of you, and especially to Thibault Damour. Permettez-moi de terminer en français pour vous dire...
Please allow me to close in French to tell you that other conferences are waiting for you. Tomorrow, Andrea Comazzo. On Thursday, Gabriela Gonzalez. On Wednesday, Claudia Duram. And on Friday, Andrew Strominger. This is also an opportunity for me to thank all those who have collaborated in organizing this event. The Wright Foundation, obviously, the University of Genève, and all those who took part in setting up this event this week. And a last point, as the rector of the university said, don't forget the fantastic Sun and Light show that takes place every evening until the 21st of November at the Parc des Bastions at 6, 7, and 8 o'clock in the evening. Go there. I think it's fantastic. I haven't seen it yet, but everybody tells me it's fantastic. Thanks very much to all of you, and see you tomorrow and the rest of the week.
Thank you very much.